let's talk about some general properties of collisions and some types of collisions that can occur in nature. We'll limit our focus to 1D, but all this can be generalized to 2 or 3 dimensions. The math gets a lot harder. In all collisions, momentum is conserved. That's true of essentially all collisions. It's in microscopic physics, when you look at subatomic particles, that is absolutely 100% true. When you have stuff that happens in the real world, like cars crashing into one another, it's still literally true. Sometimes you might have fragments of cars flying off, and it's hard to account for those. But as far as we're concerned, momentum is always conserved in collisions. Now, energy is not necessarily conserved. Again, on a microscopic level, yes, it is 100% conserved all the time. But for practical purposes, in macroscopic situations, kinetic energy is generally not the same before and after a collision. Usually it's the case that there's less kinetic energy at the end of a collision than before. So we have some vocabulary associated with the different types of collisions that can happen and whether or not energy is conserved. We say that inelastic those are ones in which kinetic energy is not conserved. Momentum, of course, is conserved. Now, there's a type of inelastic collision called perfectly inelastic. A perfectly inelastic collision is an inelastic collision in which the colliding objects stick together after the collision takes place. And just like in any inelastic collision, kinetic energy is not conserved. And momentum is. And just to be really careful about this statement that kinetic energy is not conserved, in nature, the total amount of energy is always the same. Energy is conserved, but if you're looking at two cars colliding and you just consider that system to be the two cars, the kinetic energy of the two cars after the collision is not going to be the same as before, because a lot of that kinetic energy gets turned into sound, heat, plastic deformation of the materials, and that's not energy that can easily be accounted for when you do the problem. it's still there. It didn't vanish from the universe. It's just very difficult to account for. And that's what we mean by kinetic energy not being conserved. Now, in some specialized cases, kinetic energy is conserved. And when that is the case, we say we have an elastic collision. Elastic. So both P and kinetic energy are conserved. Now, in microscopic physics, like subatomic particle physics, whenever you have colliding particles, those collisions are elastic. And in everyday life, in the macroscopic world, you can have some collisions like billiard balls, for instance, where you have objects that are very firm or very bouncy, and they return to their original shape after colliding. They don't emit much sound or heat, and those collisions are approximately elastic. You won't really have a truly elastic collision in everyday life, but you can get pretty close sometimes. Now there's a medical application that our textbook mentions. It's kind of interesting. When you have glaucoma in your eyes, that's a buildup of pressure inside the eyeball. So the eyeball gets really firm, less squishy. The eyeball gets more and more elastic. So a device called a tonometer can measure the pressure in the eyeball of a glaucoma patient. It does that by bouncing a puff of air off of the eyeball. And if you have a healthy eyeball, that collision is very inelastic because your eyeball squishes a lot, and that puff of air loses a lot of kinetic energy bouncing off the squishy eyeball. In a glaucoma patient, the eyes become extra firm. That collision becomes less and less inelastic, starts to get towards elastic. That puff of air bounces off the eyeball without losing very much kinetic energy.